It's all about cables.
Yeah, well, the story goes, I got into cables because I was looking for a job, having had a full-time job at Harman, and decided it was best not to be at Harman anymore for one reason or another.
Was that a technical role?
It was a technical role, yeah. It was technical services. I think it was called Harman International. It sounds very grand, which is actually what they called the UK company. But.
Right. So you got a bit fed up there?
And I set up just fixing stuff for studios between times. I had a new family and everything. And I thought I'd better get a proper job after having worked sort of freelance in studios and things forever. And John Goldstraw at Metropolis said, Vic, he's looking for someone, meaning Richard Vickers at Kelsey.
Oh, right.
So, you know, Kelsey manufactured cables for stadiums, studios, the whole deal. So I went up there and suddenly I was involved with cables.
Right.
And I do remember something that goes back to, I can't remember what studio it was. It might have been Matrix, where they were showing some bit of kit off. And some guy said, come and listen to this. And it's just a short patch cable. And you change the patch cable and it sounded different. And I thought, okay, now I'm not the kind of person that will dismiss something and say, oh, don't be ridiculous, or yes, absolutely. I'll say, okay, that's interesting. And I'll go away and think about and analyse it. And I kind of remembered that. And when it came to, you know, Kelsey produced millions probably of meters of mic cable.
Yeah.
And I just thought, well, yeah, what is mic cable? What's the criteria here?
Right.
And broke down the components and started looking at how those could be done better. And Kelsey got quite known for its mic cable after that. We increased.
So you redesigned their mic cable?
Yeah,
right.
absolutely.
Yeah.
And then the multi-cores. The multi-cores have got a lot of different. The multi-cores that you use for connecting, like in concerts, I have to say all this stuff for camera. So you might connect the mixing console to the stage. It's got lots of channels, you know, one for each instrument. So you might have a thick multi-core, and that's got properties. It's got to be physically strong, you know,
right?
Twisting and all that sort of stuff.
Yeah. So not only the electrical properties.
That's
but
right.
Yeah. And did it tally that if you improved measurable electric qualities, that things sounded better?
Yeah, absolutely.
Right. Okay.
Yeah. I mean, it was interesting. I thought, as maybe I hear, maybe not, and I wasn't really drilling down to be honest, that deeply into sort of special listening and all this sort of kind of stuff. But it was a chap who worked in one of the big film studios in the States. He managed to get hold of our number and rang and said, I don't know what you do, but we're in London and I've walked out with these mic cables from the studio and they got Kelsey written on them and we love them. And he's doing a library of 96K and 192K samples. Right. And he said they just sound so much better in stereo with these.
Okay.
And I thought, okay, well that's interesting because we did improve this to make it theoretically better.
Right.
But this guy's just rang from America to say he wants more of the stuff.
Brilliant.
And we didn't even sell the stuff in America, so that really got me interested in seeing how we could develop every form of cable: digital, analog, speaker, and finally power. That was a bit of a surprise, but you think, how can you improve power? It's mains, isn't it?
Well, I'd also more go back to digital because surely either it works or it doesn't.
Yeah. And when it works, how well does it work?
Well, it's like on or off, isn't it?
Well, it's not, you see. This is one thing, one of the first lessons I learnt at university was digital is actually just analog going on and off.
Right.
So how quickly does it go on and off? How in time does it go on and off?
Okay.
And you think, well, how important is that? Well, I'm going to go a slightly different route on this.
Okay.
I'm going to take a digital source, like a compact disc player.
Yes.
And a vinyl player. Now, a lot of people are saying, that vinyl sounds better than digital, which is actually sometimes it does, and that's the interesting thing. Sometimes it does, and people come up with all sorts of theories. There is one very good theory, which is background noise is there. Now, if ever you've sat in an anechoic chamber, you realise how odd it is to not have background sound. And even just opening the door a little bit to let some sound in releases something, and
it feels more comfortable. Yeah.
Interesting. I did a hi-fi show, and the sound sounded great, but there was something not quite right. And I just opened the window at the back of the room, and everyone relaxed in the room.
Yeah.
But to go back to the vinyl and digital, well, the thing about vinyl is the left and right are mechanically locked in. There can be no jitter, like the slippage of the left and right channel. Whereas in digital, you have a stream that contains the left and right, so it's been rebuilt. Now, if I had to do this, clip my fingers in front of you, if you look at the timing from the left to right ear, the shift of that, now it's quicker to get to the left ear and right ear. If you look at the speed of sound through air and the distance I've moved there, the actual change, if you like, in time is about 2 millionths of a second, which corresponds to a frequency of 500 kilohertz. So our spatial imagery, if you like, is all reconstructed from that kind of spectrum. So when people say I only hear 10 kilohertz at my age, well, that's fine, but it's the timing between what reaches your left ear and right ear is far more what's the
high
word?
Def.
To 500 kilohertz.
Yeah,
and that's well proven. There's plenty of papers out there that do this kind of stuff.
Right.
And in fact, that's how a lot of three-dimensional sound machines, if you like, that's the kind of time delays they use to create spatial imaging.
Yeah.
So it's logical that that's the spacing, the timing they're using to create 3D images. You've got to replay it to that, otherwise you would lose that information.
Yeah.
So as soon as you have digital jitter, which is kind of a disturbance in the regularity of the clock, to more than to say 100 kilohertz, well, that's massive in terms of your spatial imagery.
Right.
So yes, digital, as long as it's clocked precisely.
But does the cable quality have a bearing on the clock?
Very much so.
Accuracy.
Very much so. There's two reasons for that. When let's think, how can I tackle this one? I think cable is to transmit something down a cable. So to transmit something down a cable, what you're doing is you're energising the conductor. And the speed with which that's energised depends on a number of factors. You might have heard, certainly in the hi-fi industry, people talk about skin effect. The theory being that in a cable, high frequencies, they say, travel down the outside of a wire. And then gradually the frequencies penetrate into that. Well, that's kind of right. What actually it is when you send a signal down a cable, you're energising it. Simple as that. You put an electromagnetic field around it. Now, if you think about an analogue of that, is like a block of ice and a thin sheet of ice, the same volume, same capacity. But if you stick them in the sun, which one's going to melt quickest? Which one's going to get energised quickest?
Well,
it's the flat one.
Yeah,
it's night and day. And so the speed at which a wire energises and the magnetic field is established around it will depend on the thickness of the conductors. So one thick, chunky, solid conductor will be much slower getting energised than a lot of thinner ones, i.e. stranded cable. Also, the speed at which it gets energised is a function of the insulation around it. And you might get to the ice. If you put insulation around that ice, it's going to take a lot longer to get energised. A funny example, but then the surrounding insulation actually holds the temperature that it was at, and that will also need something to energise it. And there's a very kind of simplistic way of looking at what energises cable and not. So there's something called what we call, technically, it's the propagation delay, and that's the time it takes for the electronic signal to propagate through the wire. In hi-fi world, they call it the speed of the cable. A fast cable is really snappy, and you do get a really much clearer sort of attack.
Even with digital connections?
Well, when it comes to digital, yes, you're assuming it's going on, off, on, off, on, off, which is not. Sometimes it goes on for 3, off for 1, and then on for 1, 3 more, and then off. You know, so it's kind of random. So where the charge sits in that between that cable and its insulator, or between the two conductors, so where the charge sits between the conductor and the insulation will always vary. So the charge on it will always vary, and so you won't necessarily, even if the cable delays, if the cable is delaying the signal, it won't necessarily be an even delay on the ups and the downs. So if you get 3 downs, 3 zeros, if you like, the charge will settle much more, and then 1 quick up and 1 quick down. So you can see it starts to slew the timing.
But does that not get corrected by the clock at the other end of the cable?
In a good system, I'd have a reclocking. That's the most critical.
Surely there's a buffer that
I'd have a
collects
central
everything
clock.
and then it goes.
That's in the best world. But there's another aspect that comes into it, and that's once you start looking at how many cables go around a studio, what you're using as a grounding. Because for every force, there's a reaction that comes back, and often in a BNC cable, which is an unbalanced cable, we use the screen as the ground. When you pulse the waveform, you get a reverse coming up the grounding. It's not a static grounding. There will be a reaction, and that could go into the equipment, that could go into the earth. So to get as precise as possible does take a little bit of management of cabling.
So if there's a problem, that might affect analog things going on, perhaps, or
it's oddly enough, it's both digital and analog, and it's only, you know, that we did a number of listening tests in both digital and analog, quite exhaustive actually, and logically it doesn't make sense if you used a balanced AES cable to another reclocking balanced. We went from a Moon CD player, which is a great transport, to a Cadec CD8 digital console, fantastic console, and changing that balance cable, it just sounded much more natural.
Blind A/B test?
Absolutely, you can do blind A/B. It's so obvious that it makes it almost pointless doing the blind A/B.
And yet, scientifically,
well, no. This is where having heard the evidence, we really need to understand these things, and that's really what I've been doing is trying to understand, breaking down, looking at things like the stranding, you know, what's the tension, what are the interactions, what are the electromechanical things going on.
But surely that's what you're hearing is a deficiency in the clocking or the converter.
It can be.
Because if it's
this is the thing. Once we start looking at, say, the input circuit or the output circuit, and the cable as islands, that theory stands up. But we're joining them all together. I can have an output drive card, which is great on spec and on the bench. But once I plug it into a cable, it's then it's a synergistic thing. There's a compound thing going on that's now driving a capacitive loading. Capacitive resistive loading, which is then connected.
So, are
to
you
the other.
saying that some of these on-offs are not on when they should be off, or off when they should be on, or what are you saying is happening exactly?
Well, it's interesting if you go back to the early days of CD, as we were talking earlier. I don't know if you were there, but there was a thing that they did at Metropolis Studios, where I think in those days there were 5 CD pressing plants in Europe. Because it was a very different pressing process. It was a mechanical process, I think it was then. And you sent an exabyte, the ones and zeros, and they got all the producers and engineers, sort of invited them up, and we listened to different CD players. Now, so the equation was that there's about 8 CD players, and they'd sent the same exabyte to 5 different pressing plants. So there were 2 combinations here, you know, and they just sounded completely different. The one that sounded most natural, easiest to listen to, wasn't giving you any kind of headache or anything. Once put under the microscope, had the clearest pits embedded in it. The worst was it was much less distinct. which of course in those days the sound was all clocked.
Well,
from
that then suggests that the error correction wasn't up to much, rather than anything to do with cables.
Well, yes. To be honest, the only time I've heard very, very natural sound is when it's been reclocked all right at the end and from a master, and with a very good cable infrastructure, you have to have all those elements right.
Yeah.
It's interesting the way I look at transmission, if you like. It's getting detail from one piece of equipment to another.
Okay.
It's rather like sort of transmitting information. So I look at this as I'm drawing something very detailed on a piece of paper. So I'm really impressing the image on that piece of paper, just as a CD player would be pressing to the amplifier up and down here. And now that's very easy to do in detail. Now if I'm on a train, that's less easy to do. So I put the paper on the table and I press my hand very hard. Now what's interesting is it's still difficult because the resonance of my hand is very different to that of the table. So the information is still not getting through as clear as it might be. And it's only once you start looking at a system as comprehensively brought together and having that integrity across all frequencies that things really hang together at their best.
So up to what frequency do things need to be?
Well, I'd go back to the smallest. They reckon that the smallest, and I reckon, and all evidence is the smallest distinction we can get on a direction is about 5 degrees, and that corresponds to about, as I say, 2 millionths of a second, 500 kilohertz.
Right.
Now that's subtle. It's far easier, so 10 degrees. Now, if you listen to a stereo image, you're normally kind of roughly pointing, but even that's 15 degrees. So it depends how clear you want the separation to be. What's interesting is it seems to be a spectrum of resolution, if you like. So when you hear a very basic hi-fi, really kind of rubbish kind of digital source playing through a system, the first thing is kind of there's obvious left and right, and you hear things, and then you improve the system somehow, maybe cabling, maybe the equipment, or all of those things, and you begin to hear separation, and then people start to hear instruments they've not heard before in that mix, and then they start to hear things like the piano actually pan. Each key has a position depending how the microphone's been set up, and the more you stabilise the system with, denoise it, if you like, is all we're doing,
right,
with cabling, if you like. The better the imagery becomes. Then you get to a point where it actually starts beginning to sound more natural. And I can talk about that. That's another subject.
Okay, I'm also intrigued with when Cenzo took us around the studio. There seems to be a lot of Cat 5 going on.
Yeah.
Now that seems counterintuitive because you'd think for the best conductivity you'd want the thickest cables and certainly for guitar leads and things like that. And yet Cenzo says the clearest signal is very often a Cat 5 cable.
Yeah.
It seems very odd.
Yeah, it's not the clearest. It's the clearest budget. I would use Cat 5 more than over a multi-core, because a multi-core is, yes, there are good conductors in there, but I'd question how much current's going through that. Usually microamps. What you also have in a multi-core, traditional multi-core, is you've got a lot of insulation, a lot of dielectric, which isn't particularly well made. It's solid dielectric. It's much better to use something like a foam dielectric, which has nitrogen gas in. It's got a much better dielectric constant, i.e. back to that speed thing, transmits quicker. The other thing you have on a multi-core, which is actually quite unnecessarily, is a screen over it. People say, really? Well, the screen adds a lot of capacity, a lot of sort of electrical weight to that cable. It makes it quite sluggish. Now, on a Cat 5 cable, you don't have that. And if you question, but surely I need a screen, this is audio. Well, most networks around in the internet working at gigahertz are balanced with no screen. and it doesn't interfere, and it doesn't get
No.
interfered with.
Sluggish though. Surely electrons, when you flick a light switch, there's no. It either happens or it does. You know, it's instant. There's no varying speed of when a light comes on when you flick
Well, there
a
is
switch.
actually.
There is?
Yeah,
It's
because
not what I was taught in A-level physics.
So,
and when you so for example, if you're working in analog audio,
yeah,
and you insert something on a channel, it doesn't matter how long the cable is. If you line something up, it will phase cancel. There's no you can't get a varying amount of delay by having a longer analog cable.
Actually, you do.
I've never been able to hear that or measure it.
Yes, you could. This goes back to a conversation we had earlier about using different length speaker cables. Now, it's good you bring that up because there is something, and it's well established in the science of cable, and not just hi-fi, but across the board. It's called propagation delay, and that's the speed it takes the electrical signal to transmit down.
Right.
Yes, it's not the speed of electrons. They do move very fast. What does need to be done is when a cable gets energized, you have to pump energy into that. You have to establish an electromagnetic field around the conductors, and that takes time. That takes energy itself, like pumping it up, if you like.
So if we set up an insert on Pro Tools, which two inserts on two channels on Pro Tools, one of which was a cable that was 3 centimetres long, coming out the patch bay and back in again, and one of which went all around the car park and back in again, you would be able to demonstrate a measurable difference in the time that it took, in terms of how many samples of delay. Absolutely. I don't know about samples delay, because there's another aspect that comes into it.
I worked, when I was back with Kelsey, I worked on a golf course wiring system, and I won't say the company, but they're very well known. Because of the HF loss on the cable, they had a 15 dB gain on the console. So yes, there was loss in that cable.
But in terms of, obviously loss of high frequencies, but in terms of delay, could you measure any time change?
Yes, you would be able to.
How much? How many milliseconds?
It's normally picoseconds or microseconds. Yeah.
So enough to be able to hear a phase change if you had bass guitar at both channels.
Well, it's probably more. It's going to slightly different territory there, and this is where it becomes really interesting. And what I said, I talked about natural sound. Now, I don't know if you've ever walked along the high street, and I'll say, because I've done this many times now and noted this, but I was walking along in Sydney and I heard a saxophone, and I said to my wife, what did I say?
What did you say?
What did I say?
You didn't tell me.
So I was walking along the high street and I heard a saxophone play.
Right.
And I thought, how do I know that's real? Straight away, I haven't seen it. 200 metres away, and I know that sounds real. I was walking along the beach in Hastings. I was a mile away from the pier, and I heard a drum beat because there was a band playing there, and I knew straight away it was a live band because of the attack of that snare. Now, that really is the nub of what is natural, real sound.
Well, that's because speakers aren't very good, surely.
What do speakers do?
Well, they move the air around, but they have to handle a lot of different frequencies all at the same time.
Okay. Well, what are they not doing that they can't make that sound?
I don't know. I'm not a speaker designer, but speaker design hasn't really advanced much in the last 50 years or so, particularly. And they probably, they're not. Nobody's yet invented. If we knew what they were deficient in, somebody would have invented it.
Okay,
but you can tell that something's coming out of the speaker.
So headphones, for example. Still, it doesn't sound real. And
no, because your head moves and the sound moves with your head. So
yeah, so it's interesting because that's the kind of question I will ask, and I'll drill down till I get an answer. It might not be the answer, but it's the most convincing answer with all the evidence. Because I would say that yes, you can blame the speakers, but I'd go back to the microphone because that's also a moving diaphragm.
Yeah, and
the big deal, of course, is the attack. If you look at a microphone or a speaker or any part of it, it's the speed that piece of mechanical device takes to get up to accelerate. What is it accelerating to? That's a good question. And it's the main thing about real sound is the impact, not just the snare drum, but even in my voice, the syllables. Each most sound is a result of an impact followed by some kind of resonance, and it's the impact that has a lot. You're absolutely right. There's a lot of frequencies in there. It's called a Fourier. A compound wave, if you like, but a step wave has a pulse, a beat, has a massive amount of energy, and it has to be precisely timed. The nerves in our ears are very good at timing, at receiving and understanding that time. As I said, into 500 milliseconds. Now, if the information coming to us is out of time, if, say, some frequency is delayed, say the high frequencies, then our brain will interpret that as it not coming from that position or wherever.
But I'm pretty sure that if I ran a cable around my entire village and back again,
right,
and had another really short one, there would be nothing audibly, in terms of the timing, different. There'd be losses, obviously, of high frequencies because it's been around the village. But
well, when you say timing, are you talking about
phase difference?
Maybe not phase difference, but what really carries a lot of character and certainly, as I explained, gives us spatial information.
Is the shape of the rise time.
Is the shape of the rise time.
Right.
That's the timing I'm talking about. I'm not talking about a thousandth of a second. And it's that difference between.
Well, that's distortion rather than timing. That's because if the phase hasn't moved and the timing hasn't moved, you're talking about a distortion in the shape of the waveform rather than the timing.
Yeah, which is.
So I think it's a terminology thing, really.
Yeah, I mean we call it phase delay. So in a cable or in any.
Because electrons move at the speed they move. That's not going to change. But there's deficiencies in the cable might cause distortion.
The electrons do move, but where do they move? They're not going to appear at the other end because they've got a job to do first. They've got the first ones will go in. They will, limited by the current capacity of the source, they will have to charge up the dielectric at that point before, and so it goes down the line. So there will actually be a delay of that,
but a lot of people,
that leading edge, and that's called a phase delay. So it is actually a delay.
But you don't need that elaborate a cable to cope with the electrical properties you need for a speaker.
How do you know that?
Well, if you can measure the difference, then
how do you measure it?
I don't know. I'm a user. I'm an end user, but
because I do measure it.
Yeah.
I do look at step waves. And we do see quite big differences. In fact, the first cable we did, the Abbey Road cable, we put it was an intense thing because I worked with Abbey Road on their cabling back in '96. It was
right,
and we were building the penthouse or rebuilding the penthouse. Penthouse was where they recorded Dark Side of the Moon, so it was a bit sacred. But it was old, the studio, so it was a complete rip out.
Back to brick walls. Put
the Capricorn in, yeah. So a complete rebuild, and of course the first thing we did there was get Alan Parsons in and do surround sound of Dark Side of the Moon. So what was the point?
I don't know. Well, I was arguing that if you've got something that's electrically good enough to wire up a speaker and can handle all frequencies up until.
That's right. Okay, so.
So I use 6 amp mains cable on my NS10s.
Good for you.
And it sounds all right to me.
Great.
So what am I doing wrong?
Well, we'll get there in a second. So we'll go to this. So back to the Abbey Road thing.
Yes.
In fact, the cable that's coming out today, which so we took obviously to use the Abbey Road thing, we had to get. They had to be behind it. This is the engineers. So we did a listening test with Arnie Axelberg, who basically did a blind listening with the speaker cable. And his comment, he'd just come back from Berlin. He'd just done the Berlin Philharmonic with Daphne and Chloe Suite. Can't remember the conductor very well. The conductor, and he said the violins sound brittle again, which is exactly as I recorded them when our cable was in, and this was invigilated as well by the techies at the back, because they were like, "Oh yeah, cable, yeah, right, it makes a difference." And they were like, "Okay." And we went back to the techie room, and John, the engineer who had been invigilating, said, Arnie says we've got to put this cable in all the studios. And they go, yeah, right, pull the other one. And John said, no, really. And it was like, okay. So there is a wake-up call there. But then when we came to, there's the interesting, when we came to actually analysing on the D-scope, which is a piece of equipment which measures the quality of digital signals, we looked at the most high-frequency square waves. Don't actually look, which is how digital audio flows about, don't actually look square. They look kind of more like little mountains. And with this Abbey Road cable, they were just square. And we're talking about a reel. We hadn't even run it off the 40-metre reel.
Right.
Interesting enough, that happened about a week before I got a phone call from Cenzo when he was at Metropolis. I can't remember. I think he was working with U2 at the time, and they wanted to do a 96K, a 192, but they were having difficulty finding a cable that A, worked, and B, when it did work, it sounded okay. And the reason
cable for what? The AES?
Digital AES. Yeah. And the reason he rang me is because Cenzo, are you there? Oh no, it's fine. It's fine. Don't worry him. I can't remember the name. Paul Wilkes was the techie there. I dropped a roll of this cable into him just to try, and sort of pulling their hair out trying to get this 192. They came with a roll and they just put an XLR at either end of it, plugged it in, and it sounded superb. And Cenzo rang me and said, "Can we have more of that cable?" The point being, on the D-scope, we were just getting these square waves on.
So what do you do to make it do that? Or is that a trade secret?
Not a trade secret. We just look at what the job is of the charge that needs to go and how quickly can we charge that, and how can we get the dielectric as sort of least greedy and soaking up what it needs as possible, because obviously that will speed up. And
so is this metallurgy, or is this...
Not really metallurgy, it's more mechanical and design.
Right.
We've done an extensive amount of research into the types of cable, and this means making exactly the same dielectrics, the whole thing, but with different metals inside. And I've not heard a difference in the actual metal. In how it's stranded and the tensions and things like that, yes, absolutely.
Okay. Right.
But that seems to say that there's an electromechanical thing going on. It might be microphonics. It might be actually between two conductors. There's an electroforce, and if any mechanical vibration takes place, doesn't matter how small it is, there will be energy dissipated and a small phase change at that frequency because of that mechanical vibration. So which brings us back to the speaker cables. I'm not one who believes in stuff until I've really analysed it. Yes or no, people say it makes a difference or it doesn't make a difference. I said, well, there's enough in the world that have said there is, and there's enough that haven't. So let's look at that's an interesting thing. Let's look at the circumstances that it is making a difference, and then the circumstances that it's not. It's only when you start to analyse things to that level that you begin to put a story together. Back to sort of cable wizardry or magic or pixie dust, if you like, is the idea of cryogenically treating cable. Some people swear it makes a difference. Now, I've heard it. Okay, yeah, it's kind of subtle, but it's there.
Right.
Which you can argue, but it's the reasons that people then attribute it, which I think is quite funny. Because it makes a difference. I know, it must be the crystals aligning in the copper. I think, well, copper's not that crystalline. It's very granular. There are crystals, but they're random sizes, and they're really bunched together. So I don't know how they're aligning. So, you can get a piece of copper and treat it, and a piece that doesn't, and lo and behold, no difference. What's interesting when you look at the whole picture is you have a piece of copper that's been extruded. You then have some plastic extruded onto it at high temperature, which then contracts onto the copper. So there's a temperature difference as it cools. So there's a lot of stress in that dielectric. It's binding very hard to the copper itself.
Right.
Which will change two things. When, as I said earlier, there are faster dielectrics. Air, nitrogen is the best dielectric. Nothing. The best conductor is a pipe. There's a lot of surface area and there's nothing around it to sort of slow it down. So when you get this copper that's got this extrusion of plastic on it, that's going to be really in very tight contact. Now, of course, once you freeze this, when we freeze plastic, even below 30 degrees, it becomes extraordinarily brittle, let alone minus 200. The plastic will fracture microscopically and break, and the tensions will change.
I see.
So when you then thaw it, there's going to be little spaces. And that will change not only the electrical but any mechanical properties there as well. The other consideration is when you extrude a plastic, there's an immense amount of static built up in that. It's a very good insulator at high temperatures as it's cooling down, which of course when you freeze that to such low temperatures it becomes much more conductive, as most things do become superconductive, which gives an opportunity for any static that's built up in that to dissipate a little bit. Maybe, maybe not. That maybe is out there on left field. But
what about sexing cables, turning them around the other way? Does that make a difference?
If it does, there's something wrong in your system.
That's when I stopped reading hi-fi magazines.
I think if that's happening, then they say that the word is diodic, which means it makes something go one way better than the other. If you have a cable that's doing that, get rid of it.
Right. Because that was all the rage in the mid-1980s in hi-fi news.
And yeah, absolutely. I would ask why. That's designed very badly. I don't want a cable that does that.
Well, so that's when I stopped, because I was, I got the job in the studio. And we were using ropey old Bantam cables, and I thought, really?
Yeah. Especially as it's alternating current, which means it should equally be going one way than the other, as it is to the other. Yeah.
And are there snake oil salesmen in the cable business?
Absolutely, loads of them. It's been the hardest thing. Cable was cable. It was copper and plastic for a long time, and then people started to make quite good cables. Now, if you go to other industries or other areas, you will find that there are techniques which have been developed which really do help. An example of this is actually when I first got the first Abbey Road cable made, we used foamed polyethylene dielectric. This polyethylene is a good dielectric, very low dielectric constant, which means it's quite fast. Nitrogen is the best. It's the benchmark. It's zero, if you like, in terms of delay. So yes, we could use Teflon, which is slightly better than polyethylene. But guess what? You can foam polyethylene, you get 40% of nitrogen there, and its dielectric constant becomes much better. Also, you get little bubbles between the conductor itself and the dielectric, the insulation, which is yet another improvement. However, when we first did this, to get it done in time for the Abbey Road test, the listening test, which was set for the Monday, I phoned the factory, and it was Wednesday, and they hadn't got this on the machine, the special foaming machine. And the only other foaming machine we knew about was in Barcelona. And this is how much your technology does involve what we do. And this is how long the technology's been going around, because that factory was built by the Axis during the war to build high sensitivity radio aerial cables so they could spy on the Allies.
Right.
So we used that machine to make the first cables, and it works. It works. It worked for the Axis. The Axis of evil.
So how do you tell a snake oil salesman in the cable business?
I look at science. There's I was at a show. There's every year in Munich. There's an impressive the world's sort of main hi-fi show. There's hi-fi and there's really good sound systems there. And the science has actually got better over the years, probably since you last looked at a magazine. I don't know how long ago, but there is a lot more science behind it now, which is a good thing. But there's a lot of people who are kind of winging it as well, and you can't wing science.
No, well, this is you do see some funny descriptions of things.
This is alignment of crystals in copper territory. And
it's very difficult for somebody like me to differentiate, because
absolutely,
you know, I've borne witness to hi-fi tweak stands and things and heard amazing differences.
yes.
But then some of the other things in the same catalogue are clearly nonsense.
Yeah. I think what's interesting is, as an engineer, a technical engineer, is to drill down the essence of what is actually happening. Yes, spikes in the floor can help. That doesn't mean all spikes in all floors and all equipment will help. And it's not until you understand why that's working, if it's removing some kind of resonance frequency, then you can say, okay, so is there a resonance frequency on that we want to get rid of? Is the first question. If there is, what frequency and how do we do it? So it becomes much more an informed process, rather than gambling.
There needs to be perhaps some sort of certification process so that you can...
yeah.
Because if I started looking into all this, A, I wouldn't understand half the science, and B, I'm more interested in whether the song's any good, and you know, whether it needs a bit more treble on the hi-hat.
Absolutely.
And if I got distracted by cables, so, you know, and it's when we talk to Cenzo, he doesn't profess to have any scientific knowledge about cables, but he trusts you and he's heard the difference. So, whoa. So it's an interesting question, isn't it? Because how do you ascertain what is real and what is fake?
Yes. Yeah, well, I can do that from a scientific point of view, which most people can't. So the only way I can do it...
That's why I'm sort of trying to sort of... Obviously, I'm not technical enough to be able to express it very well, but that's why I'm saying, you know, when I'm talking about the timing, to me, is when something arrives.
Yeah. And
from my distant memory of doing A-level physics,
the
electrons travel all at the same speed.
Yes, except they have... in cable, they've got work to do.
Well, yes, so you say.
And that takes time. You know.
But you understand my scepticism.
Absolutely. So, you know, if I have a mile of cable, let's say, and I need to get a charge into that cable in order to switch the light on at the other end, the electricity will go in there and it will see an empty space, a void it's got to charge first. So there will actually be...
Yeah, obviously, because there's a capacitance to the cable.
Absolutely.
Yeah, no, I understand that. Yeah, sure.
So, yeah, exactly. It's a capacitance that needs filling.
Yeah.
Or charging.
And it's how... It's it's the boundaries of where that makes a difference, and what as you say, the frequencies. If you need to be up to 500 gigahertz, then
this is what's interesting. Is that seems to be, I suppose there are different compass points. At first, really kind of basic north, south, east, west is, can I hear stereo? Yeah, that's great. I've got left and right. And then when you drill down,
that's usually good enough for me.
Cut that. But it's when it's interesting because one of the two factors I find at the finest precision of sound is, one is the attack, the snare drum, but the other is actually the female voice, the higher notes. Whether in a system that's not working, it seems to be an accentuation of syllables which you don't hear in real life, sharpness, and it's really that disappears when things are right. Now that goes back to Mr. Fourier. Now the interesting thing about any impact, which is most instruments have some kind of impact. Voices do all the time. All the syllables are impact. An impact will, in terms of the pressure wave coming, there'll be no pressure and there'll be a sudden rise in pressure. And that's quite important because our ears don't respond to the same way to a drop in pressure. So it's important to get a relative phase. We're not wired to do that. We respond much better to a positive rise. Now, an impact is a singularity. It goes up. As I said, there's a lot of frequencies in that. Now, the interesting thing about a way to look at that or imagine it is, if there are all these frequencies in there, they need to be reproduced. Think of it going backwards in time. All those frequencies, all that energy has to instantaneously stop. Because if any are delayed, then it won't be as an impact from the thing. So that's a way of kind of trying to understand how important it is that the whole spectrum of frequencies are aligned to give that impact. I don't know if that's enlightened you at all, or just confused you.
No, I think that's
the first time I've explained that to anyone.
Well, that's very, very well done. No, I think that makes sense. Yeah. Although I don't listen to many things backwards these days.
No,
those
it's a bit 80s.
dope smoking days are over. Yeah.